Let's talk about orientation. So orientation gives our parameterization a notion of what the top of the surface is and what the bottom of the surface is. It tells us what direction the flux is moving. And if our surface is broken up into multiple pieces, if we want to get a consistent calculation, we have to make sure that those match up. So for example, we might be asked, let's calculate the total flux of this vector field, f of x, y, z, out through the surface of the cylinder, given by x squared plus y squared is less than or equal to 1, and 1 less than or equal to z less than or equal to 4. So this is a cylinder where we've got a kind of round surface that goes around the z-axis, but we've also got caps at the top and the bottom. And if we're calculating the total flux out of that surface of the cylinder, we have three pieces. We have to account for the flux out through the top, the flux out through the bottom, and the flux out through the sides. And so when we do that calculation, we have to make sure that those match up, because they each come with their individual parameterization. Now, here's one I prepared earlier. So here we've got three different calculations of flux through the surface. This one at the top is the top of the cylinder. This one on the bottom is the bottom of the cylinder. And this one in the middle comes from the sides. I'll talk a little bit about what's going on in here because this is a bit of a mess. For the top of the cylinder, that's given by z is equal to 4. So my parameterization is phi of uv is u comma v comma 4. It's basically the graph of the function z equals 4. And so I can use my shorthand formula for the normal vector. The shorthand formula for the normal vector says I should put the negative derivative of 4 with respect to u in the first component, and I should put negative derivative with respect to v of 4 in the second component, and I should put 1 in the third component. That's my normal vector. Then I evaluate what my vector field is doing at the point u comma v comma 4, and because my vector field had the formula f of x, y, z is equal to x, y, z, I'm basically just firing the same thing back out again. And so then I take the dot product of those two things, my normal vector with my vector field, and that gives me the number 4, and then I integrate it over my region of integration, which in this case was a circle, and that gives me 4 pi. The bottom is very, very similar, except that my parameterization is u comma v comma 1 to give me the bottom of the cylinder. My normal vector is basically the same. My vector field is calculated similarly. I take their dot product and now I'm integrating 1, and that gives me a total contribution of pi from the bottom. For the middle, I use a parameterization from cylindrical coordinates because it's a cylinder. And here's my parameterization. Phi of uv is cos u comma sine u comma v. Here are my tangent vectors. The derivative with respect to u is minus sine u comma cos u comma 0. My tangent vector with respect to v is 0, 0, 1. My cross product is cos u comma sine u comma 0. My vector field at the point I'm interested in is cos u comma sine u comma v. The dot product of those is going to be cos u times cos u plus sine u times sine u plus v times 0. That's cos squared plus sine squared, and gives me 1. So that integral is going to be 6 pi. And normally, during teaching this class, this would be kind of an event, like doing this integral would be a day and we would work through it slowly. Instead, I've had to prepare it earlier and then draw and red all over it. What have we done here? We've calculated that the total contribution from the top was 4 pi, the total contribution from the bottom is pi, and the total contribution from the middle is 6 pi. But we need to check orientation. We're trying to calculate the total amount of flow out. So for the top, my normal vector was 0, 0, 1. 0, 0, 1 points in the positive z direction. So that's perfect. That is calculating flow out of the cylinder. For my parameterization in the bottom, my normal vector was 0, 0, 1. That's not pointing outwards. That's pointing inwards. And so it's calculating flux in the direction opposite to what I want. And so 4 pi is the contribution that I'm getting for flow outwards on the top. To get the correct contribution for flow outwards on the bottom, I need to switch it to a negative sign because my normal was pointing in the wrong direction. For the middle, my normal was this, cos u comma sine u comma 0. That's what we calculated when we calculated tu cross tv. And so I have to figure out, is this normal giving me the right answer? Is it giving me the wrong answer? Is it going outward or inward? So we have to check. And there are a couple of ways to do this. One of them is to just kind of plug in a point. If I plug in u comma v is equal to 0, let's say 0 comma 1, that's a point on the bottom edge that would give me the point x equals 0, x equals 1, y equals 0, z equals 1. And then if I plug in the normal vector, I would find that the normal is pointing this direction. So I could just plug in one point, and that could be used to tell me what the normal vector is. Or I could instead use some understanding of what my thing was doing when I was doing cylindrical coordinates. When I was doing cylindrical coordinates, I was saying u is basically equal to theta and v is equal to z. So as u increases, I move around in a counterclockwise direction, and as v increases, I move upwards. So my tangent vectors in the u direction and the v direction are pointing horizontally and vertically like this. And so I can figure out what their cross product is using the right-hand rule. The cross product of those two, if I point my thumb in the direction of tu and my index finger in the direction of tv, my middle finger tu crossed with tv points outwards from the cylinders. And so this is oriented correctly. And so I get a contribution of plus 6 pi and plus 4 pi and minus pi. So the total flow outwards is 9 pi. So orientations are important. We have to make sure that we're consistent with them if we want to get the right answers for these types of questions. So finally, there's one more warning. Some surfaces are completely impossible to do this with. They're called non-orientable because there's no consistent way to do an assignment of up and down to the entire surface. For example, a Mobius strip is a famous example where it has only one side, and one way to see that is if we kind of take ourselves and imagine kind of trying to follow a normal vector around the outside of this surface. As it moves around, it kind of starts to flip over and eventually comes to pointing in the opposite direction when we come back around to the beginning. This means that calculating flux through these surfaces isn't really that meaningful because we can't consistently assign direction. It doesn't mean anything to say that this is flowing upwards or downwards for the Mobius strip because the Mobius strip doesn't have an upwards or downwards. We don't typically encounter this type of problem, but it's something to be aware of. We need to be able to have a consistent orientation for the entire surface to have a meaningful answer for a flux integral.